Okay, so today we're going to move on to look at trig limits. Remember, we did some trig limits way back in chapter 3 at the beginning of second semester. One of the things we're going to look at today is recalling the special trig limits. Remember, the special trig limits are very helpful. It's not special like what my mom used to call me when I was a kid. She also used to tell me I was handsome and smart too. But I digress. Anyway, special because if we can understand these trig limits, then they help us be able to analytically evaluate many other trig limits. Okay, so let's get into some practice. So here I have the limit as x goes to 0 of sine of 1 over x. Alright, I also included a graph here so we can kind of get a pretty good idea of what's going on. So we can see from the left and from the right on the graph, as I get closer to 0, it appears that the graph just gets all jumbled. So, well, exactly what is happening? Well, if we plug in values, so we could do this on a table on our calculator, but because we understand the sine function pretty well, we can do this without a calculator. So think about values of sine that you know. Well, for example, all of the pi halves values. We see if we try to do direct substitution, we end up with the sine of 1 over 0, which we can't do 1 divided by 0. So can't do direct substitution. Let's plug in values that are going to get close to 0 but not exactly 0. So I'm going to use all of the pi halves values. Now the thing I want to recognize is, since this is 1 over x, I don't want to plug in pi halves. I want to plug in 2 over pi, and then 2 over 3 pi, and 2 over 5 pi, and 2 over 7 pi, and so on. And now, if I evaluate sine of 1 over x at those values, I'm going to get a y value of, well, what is the sine of pi halves? Sine of pi halves is 1, 3 pi halves is negative 1, 5 pi halves is 1, 7 pi halves is negative 1, and so on. And so these values, 2 over pi, 2 over 3 pi, 2 over 5 pi, 2 over 7 pi, those values are getting close to 0 from the right-hand side. You should hopefully be able to understand that I could also do this from the left-hand side using negative 2 over pi, negative 2 over 3 pi, negative 2 over 5 pi, negative 2 over 7 pi. It's going to give me the same values, or I should say it's going to follow the same pattern, that basically the numbers are going to keep jumping between 1 and negative 1. What does that tell me? That is telling me that the limit does not exist. And that's kind of what I see going on in this graph here. It's hard to tell exactly from the graph because, remember, our calculators aren't limited to how much they can actually show us. So because this jumping between 1 and negative 1 is happening so quickly, the calculator doesn't show it very well, but it does show us that something's going on here that's not going to produce a limit. Alright, what if we change this slightly? What if it becomes the limit as x goes to 0 of x times the sine of 1 over x? Well, now what does this x do to the function sine of 1 over x that we didn't have in the previous problem? Well, now I can see if I look at the graph, it does appear that I am approaching a limit. It appears that the limit is 0, and that is going to be our answer as well. But let's talk about why is that. Well, a couple of things we want to mention. First, recall back from first semester, dampening. So the x is causing the function sine of 1 over x to dampen. We know from the previous example, sine of 1 over x is going to bounce back and forth between 1 and negative 1. But as x gets small or close to 0, then I'm multiplying those very tiny numbers by 1 and negative 1, so they are also becoming tiny, or approaching 0. The other thing that we can use to help us understand this is, again, something we talked about back in chapter 3, at the beginning of second semester, and that is the squeeze theorem. So remember, same thing as before, I don't expect you to necessarily be able to come up with the functions that are squeezing, but I do expect you to understand the concept of the squeeze theorem. So if I have some h of x, this is less than or equal to f of x, which is less than or equal to g of x, and I know the limit of h of x as x goes to c equals the limit of g of x as x goes to c, then I know the limit of f of x as x goes to c has to also be that value. So that's our squeeze theorem. So if I look back here, well, because of this dampening factor, the function is dampened by the line y equals x and y equals negative x. But another way that I can write that to help me see the squeeze theorem is I know that negative absolute value of x is less than or equal to x sine of 1 over x, which is less than or equal to the absolute value of x. And I can visually see that here in this, so here's the same function, but now, let's see, this line here, this would be the absolute value of x, and this line here, that would be negative absolute value of x. And so at 0, I can see that those are going to equal 0, and therefore x sine of 1 over x is also going to equal 0. Here's another visualization using a slightly different function, but same idea. The limit as x goes to 0 of x sine of 10x. What does the 10 do? Well, it changes the period of the sine function, but it doesn't change the limit of this entire function. So this is still going to equal 0 for the same reason as the previous one, that in this case I know, same thing, negative absolute value of x is less than or equal to x sine of 10x, which is less than or equal to the absolute value of x. Again, the big thing with these examples is I want you to understand visually how to figure out the limit and understand that the squeeze theorem does apply. You don't need to necessarily come up with the functions that are doing the squeezing. Okay, so let's move on to some more analytical examples. I want you to pause the video and evaluate each of these limits. It should be pretty straightforward. You're going to use direct substitution for all of them. So pause the video, unpause when you're ready to check your work. Okay, so here we should plug in 0. The tangent of 0 is 0. Therefore, the limit as x goes to 0, tangent of x is 0. For the second one, if I plug in pi, I get pi times the cosine of pi. The cosine of pi is negative 1, so this is negative pi. The limit as x goes to 0 of sine squared of x, sine squared of 0. The sine of 0 is 0, so if I square that, that's still 0. Okay, hopefully that's pretty straightforward. We recall direct substitution. That's the first thing we want to go to. Special trig limits. Remember, this is our big one. We want to, or we already have this memorized. The limit as x goes to 0 of the sine of x over x is 1. I can see that from the graph. Remember, I also showed you a version of, or a proof of this using the squeeze theorem and geometry, or the area of triangles and sectors. But we want to know that the limit as x goes to 0 of sine of x over x equals 1. We want to be able to do this without our calculator. Okay, I want you to evaluate the limit as x goes to 0 of tangent of x over sine of x. I will give you a hint. You're going to want to use some trig identities, because when we first do direct substitution, we get 0 over 0, which is one of our indeterminate forms. So we need to do something else. Use your trig identities, help yourself, and then find the limit. Pause the video, unpause when you're ready to check your work. Okay, so we should end up with the limit as x goes to 0 of tangent of x over sine of x is 1. How do we get that? Well, first I used my quotient identity to substitute in for tangent of x, so that it became the limit as x goes to 0 of sine of x over cosine of x over sine of x over 1. Multiply by the reciprocal of the denominator, So I get the limit as x goes to 0 of sine of x over cosine of x times 1 over sine of x. Sine of x's cancel, and I'm left with the limit as x goes to 0 of 1 over cosine of x. Now I can do direct substitution. The cosine of 0 is 1, 1 over 1 is 1. Fantastic. Next one, or next two I should say. Evaluate the limit as x goes to 0 of tangent of x over x, and then evaluate the limit as x goes to 0 of sine of 2x over x. I'll give you two hints, because both of them you end up with the indeterminate form originally. For the first one, you're going to need to use your special trig limit, the sine of x over x. For the second one, you're also going to need to do that. However, to come up with that, you are going to have to figure out what to multiply the numerator and denominator by to create the special trig limit. First one, you're going to have to use a trig identity. Pause the video, unpause when you're ready to check your work. Okay, so the first one here, this is actually something we did again back in chapter 3. So we got the indeterminate form. Okay, now what? Well, let's substitute tangent using our quotient identity again. So that's sine of x over cosine of x over x over 1. So then this becomes the limit as x goes to 0 of sine of x over cosine of x times 1 over x. Well, if I regroup this, remember the numerator is all multiplication and the denominator is all multiplication, so the order in which I do it does not matter. So I'm going to bring the x in front of cosine of x. So this becomes the limit as x goes to 0 of sine of x over x times 1 over cosine of x. Well, I know the limit as x goes to 0 of sine of x over x is 1. The limit as x goes to 0 of 1 over cosine of x is 1. 1 times 1 is 1. Bam. Next one. This one's a little more tricky. So we got the indeterminate form again. Now I have to figure out what can I multiply the numerator and denominator by to create my special trig limit. So one thing to keep in mind is when we're looking at the special trig limit, it doesn't matter that these both be x. What matters is that they're the same thing. So it doesn't have to just be x. So in this case, I multiplied by 2 times sine of 2x in the numerator and denominator. And what that did is when I distribute how I want to, this 2 times that x became this 2x. Sine of 2x is this sine of 2x. This 2 I just kind of left in front. The sine of 2x in the denominator is this. So now here I'm taking the sine of the same thing on the top that I'm dividing by on the bottom, and here I'm taking the sine of the same thing on top that I'm dividing by on the bottom. So I'm essentially grouping this. The limit as x goes to 0 of that is going to be 1. The limit as x goes to 0 of this is going to be 1. And then the 2 just stays there. So I have 2 times 1, which is 2. Good stuff. Alright, so the trick there again, though, is to try to figure out what am I taking the sine of in the numerator and get that in the denominator. If you end up with some extra constants, that's okay. Alright, next one. Find the limit as x goes to pi halves of sine of x over x. Pause the video, unpause when you're ready to check your work. Okay, hopefully this one was much easier. You just use direct substitution. Don't get so caught up in that you have to do something special and create a special trig limit every time. Sometimes there's easy ones as well. Next, you've done this before, but I want you, if you don't remember, prove that the limit as x goes to 0 of 1 minus cosine of x over x equals 0. So again, you have to create the special trig limit using sine. Pause the video, unpause when you're ready to check your work. Okay, so what we need to do first here is somehow come up with a way that we can introduce sine into the function. So to do that, multiply the numerator and denominator by the conjugate of the numerator. We end up with 1 minus cosine squared over x times 1 plus cosine of x. 1 minus cosine squared is sine squared. Split this up into sine of x over x times sine of x over 1 plus cosine of x. Now I can evaluate the limit. Sine of x over x is 1. This becomes 0 over 2. 1 times 0 over 2 is 0. Okay, so we want to make sure we recall our special trig limits. You already know them, but we also want to recall our trig identities. understand the squeeze theorem and be able to evaluate trig limits analytically using direct substitution and trig identities.